We're now going to talk about the difference between strong and weak acids and bases. So in chemistry, strong acids and bases mean that they completely dissociate, meaning that they break apart into its ions in an aqueous solution. So an example of a strong acid is hydrochloric acid. Hydrochloric acid will completely dissociate into the hydrogen ion and a chloride ion, whereas a weak acid will not dissociate completely. Only a small percentage of it will dissociate. An example of a weak acid would be acetic acid. Acetic acid usually just stays whole as one complete molecule, and only some of it will completely dissociate. And so therefore acetic acid is a weak acid. So if it's a strong acid or base, that means that it will completely dissociate into its ions. Weak acids and bases stay together when they're in an aqueous solution. So in chemistry, we have 7 strong acids that are known and that you need to know. The 7 strong acids that you need to know are hydrochloric acid, which is HCl. And remember, acids are always aqueous, so this is hydrochloric acid. The other 6 are HBr, or hydrobromic acid, hydroiodic acid, which is HI, nitric acid, sulfuric acid, chloric acid, and perchloric acid. So these are your 7 strong acids, and what that means is that they will completely dissociate. HCl will dissociate into the H plus ion and the chloride ion. Sulfuric acid, being a strong acid, will dissociate into 2 hydrogen ions and the sulfate ion. And so each one of these acids will completely dissociate, and that's what makes it a strong acid. Now what about bases? Which bases are strong? Well, we can look at the periodic table to help us with that. Your strong bases are bases, the hydroxides bonded with lithium, sodium, potassium, rubidium, and cesium. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, as well as calcium, strontium, and barium. So the first column, the alkaline metals, and then the alkaline earth metals starting with calcium and going on down, are all strong bases. That means that the hydroxides of these metals will completely dissociate when dissolved in water. Now whenever you have an acid and base react together, this is what we call a neutralization reaction, which is a type of double displacement. And so a generic double displacement reaction is where we have the compound AB, where A and B are ions of some sort. They can be monatomic or polyatomic ions, along with CD will react to make AD plus CB. Now let's look and see what I did here. I took this A and I bonded it with D to make AD. So basically what I'm doing is I'm flipping the A and the C with each other to make new compounds. ABCD turns into AD and CB. So the A is now with D and the C is now with B to make 2 different compounds. And so this is what we call a double displacement reaction. It's also called a metathesis reaction, which you may see that occasionally. So how does this play a role whenever we have an acid and a base? So let's do HCl with sodium hydroxide. So here we have a strong acid, meaning it completely dissociates, and a strong base, which also completely dissociates. Now what we're going to do is we're going to basically flip the H and the sodium. The hydrogen and the sodium are going to switch places. The sodium is going to bond with the chlorine, and the hydrogen is going to bond with the hydroxide. And so we end up with NaCl, the sodium comes over to Cl, and then a hydrogen goes to the OH to give us HOH, which we can also rewrite as H2O because that's simply water. So whichever way, it doesn't really matter. But in this case, this is a neutralization reaction because what happens is we have an acid and a base react together to make a salt and water. Now let's do another more complicated one. Let's look at nitric acid reacting with potassium hydroxide. So nitric acid is a polyatomic acid, and so what we're going to do again, we're going to flip the 2 metals, the hydrogen and the potassium. The hydrogen is going to go with the OH, the potassium is going to go with the nitrate. And so we end up with potassium nitrate and water, or HOH. And so this is a neutralization reaction. We have an acid and a base making a salt, in this case is potassium nitrate, and water. Now some neutralization reactions can produce a gas, and let's look at an example of that. So a reaction that you probably have done in the past is baking soda and vinegar. So the formula for baking soda is sodium bicarbonate, which is NaHCO3, and then we're going to react that with vinegar. And vinegar's formula is HC2H3O2. So this is the acetate ion and then hydrogen. So when I'm forgetting to put the aqueous, all of these things are actually dissolved in water. Water is always still present. I'm just being a little bit lazy here and not putting aqueous symbols here, but they're all always dissolved in water. And so the sodium is going to flip places with the hydrogen, just like what we did up here. And so we're going to end up with sodium acetate, and the hydrogen is going to go with the bicarbonate ion. And so we're going to end up with Na, so sodium with the acetate, C2H3O2. And then going on to the next line, the hydrogen is going to go with that to be H2CO3. Now this right here is carbonic acid. Carbonic acid is an acid that easily decomposes in water. And so what will end up happening is another reaction occurs. So that sodium acetate stays as a product, and that carbonic acid ends up decomposing. So let me rewrite the sodium carbonate. That should be a 2, not a 3. So NaC2H3O2 plus, and then this is going to decompose into carbon dioxide and water. Carbonic acid always decomposes into CO2 and water, and that's what makes the bubbles form whenever you do this volcano reaction of baking soda and vinegar. Now we talked about strong acids and strong bases, weak acids and weak bases based off of how much they dissociate. So how do we figure out the concentration of an acid? And so one way of determining concentration of acid is how much hydrogen is produced. All these acids are dissolved in water, and so they will produce the hydrogen ion. That's what defines it as an acid, at least as an areneous acid. And so the hydrogen ion being produced. So the more hydrogen ion that's produced, we could say the stronger the acid is. And the way we measure the strength of an acid, or I should say not necessarily strength, but the acidity of an acid, is through something called pH. pH stands for the power of the hydrogen ion. And so this is actually a log function, but all you really need to know is that the pH is a scale that we use to measure acid, or measure acidity or alkalinity. The pH scale runs basically from 1 to 14, where 1 is an acid and 14 is a base. So if a substance has a pH of, let's say, 1, 2, or 3, it is going to be acidic. If it has a pH of 12, 13, or 14, it's going to be considered basic. Now the middle of the scale is 7, and at 7 we consider that to be neutral. That means that the amount of the acid and base are basically equal to each other. The hydrogen and the hydroxide are equal to each other, and that is essentially pure water, and so we define that as a pH of 7. So anything below 7 is going to be an acidic solution. Anything above 7 is going to be a basic solution.